let's jump right into this. Welcome to today's explainer, where we're going to look at mechanical ventilators from a completely different angle. Think about it. I want you to imagine a mechanical ventilator not just as, a standard medical device, but as a highly complex vehicle. And right now, we're basically forcing clinicians to fly this vehicle manually, making continuous high-stakes adjustments around the clock. What this vehicle desperately needs is an autopilot system. We're talking about a smart, safety-first framework that actually adapts in real time. So today, we're unpacking a really fascinating proposal for exactly that. And we're going to focus heavily on the esophageal pressure's role in safety and precision critical care.
Here's how we're going to break this all down. We'll start off by uncovering the hidden dangers of ventilation, then we'll introduce our primary safety sensor. After that, we'll look at the glitches that happen when the machine and the patient clash, unveil this proposed closed-loop autopilot, and then finally, we'll bring it all back to reality with the next steps required to actually get this tech into the ICU. All right, kicking things off with part one, the hidden dangers of ventilation, or as it's sometimes called, the ventilation paradox. Let's start with a medical paradox that sits at the very heart of modern intensive care. So you gotta ask yourself, how can a life-saving machine also cause severe injury? It's a heavy question, right? We all know ventilators save lives, absolutely. But the stakes for safety are just incredibly high. The very pressure used to inflate the lungs can actually cause ventilator-induced lung injury, or VILI. And if the machine does too much or even too little work for the patient, it can lead to ventilator-induced diaphragm dysfunction, or VIDID. Add in patient self-inflicted lung injury, and you literally have a perfect storm. The clinician's ultimate goal is to protect the lungs and the diaphragm at the exact same time. But trying to do that with only standard airway pressure readings, it's kind of like flying blind. Okay, so to really make sense of this, we need to nail down one key concept: transpulmonary pressure. Basically, this is the airway pressure being pushed in minus the pleural pressure outside the lungs. So why does this matter? Well, because transpulmonary pressure represents the true, actual stress being delivered to inflate those fragile lungs. If we want our ventilator autopilot to actually keep the patient safe, this is the foundational metric it absolutely must track in real time. Moving right along to section 2, the esophageal safety sensor, or as I like to think of it, the body's LiDAR. So how do we actually get that pleural pressure measurement to calculate the true lung stress? The answer is esophageal balloon manometry. By placing a specialized catheter with a tiny balloon on it down into the esophagus, we get a highly reliable surrogate for pleural pressure. Think of it like a high-tech LiDAR sensor for the body. It essentially allows us to partition the mechanics of the lung from the mechanics of the chest wall. I really want to emphasize that esophageal pressure's role in safety cannot be overstated here. It is the clinical gold standard that unmasks the patient's true inspiratory effort, allowing us to calculate that vital transpulmonary pressure we just talked about. Which brings us to part 3, fixing ventilator dyssynchronies. Basically what happens when the machine and the patient crash into each other. Now that we have our safety sensor, let's look at the chaotic traffic jams that happen when manual settings clash with natural breathing. Now, when things are perfectly in sync, it's actually pretty amazing. You get this beautiful harmony between the human and the machine. The exact moment the patient starts their effort, which shows up as a little negative dip in the esophageal pressure, the machine instantly triggers. And then, during the cycling phase, the machine seamlessly lets the patient exhale exactly when their effort naturally ends. This kind of harmony is our ultimate goal, but unfortunately, this isn't what always happens. In reality, things glitch. We call these glitches dyssynchronies, and they can affect up to 30 to 40% of ventilated patients. Actually, some reports say literally 100% of patients experience them at some point. You've got missed or delayed triggers, which is when the machine just completely ignores the patient's effort. Then there's double triggering, which is incredibly dangerous. That's when a sustained patient effort causes the machine to fire twice in a row, breath stacking and doubling the tidal volume, which severely increases the risk of lung injury. There's also reverse triggering, auto-triggering from cardiac artifacts, the list goes on. Fixing these constant glitches is exactly why we desperately need automation. All right, let's get into the really exciting stuff. Section 4, the closed-loop autopilot, the Level 5 autonomous ventilator. This right here is the core proposal of the source paper, moving away from constant manual tweaks to a fully automated, safety-first theoretical framework. Let's break down how this builds into an actual working architecture. The proposed closed-loop system runs 3 parallel layers right inside the ventilator's microprocessor. First up, the lung protection controller continuously adjusts airway pressure and PEEP to keep those transpulmonary pressures safe. Second, the The synchrony controller uses the esophageal signal to trigger and cycle breaths exactly to the patient's neural timing, which completely eliminates those dysynchronies we just talked about. And third, the diaphragm protection controller modulates support to keep the patient's muscle effort in a healthy, safe range. When you map out the macro logic of this entire setup, it's pretty wild. You've got this continuous stream of data from the esophageal balloon feeding directly into the dual pathways of lung protection and diaphragm protection. But the main thing I want you to take away from this logic is the overarching rule: safety always wins. The algorithm is built with super strict conflict resolution. If achieving a certain lung recruitment target would push the transpulmonary driving pressure too high, boom, the algorithm initiates a priority override. Driving pressure safety limits always take precedence.
So what does this look like in practice? Well, the automated system translates all those physiological parameters into hard, actionable targets. It constantly adjusts the applied airway pressure to keep the inspiratory transpulmonary pressure safely below 20 to 25 centimeters of water. It constantly tweaks PEEP to keep the driving pressure in a really tight 10 to 12 centimeter limit to prevent lung injury. And then there is the patient effort, or PEMAS. 3 to 15 centimeters of water. I really want to highlight this specific number because this is the absolute Goldilocks zone for patient muscle effort. Think about it. If the ventilator gives too much support and the patient's effort drops below 3, they risk rapid disuse atrophy of the diaphragm. But if the ventilator gives too little support and the effort spikes above 15, they risk load-induced injury. By anchoring the algorithm to this safe range, the autopilot guarantees true diaphragm protective ventilation. Okay, time for a reality check. Section 5, reality checks and next steps. The roadblocks to autopilot. Because it sounds incredible, right? But if esophageal pressure is such a physiological superpower, you might be wondering, why aren't we already using this autopilot everywhere? Let's ground this theory in some reality. The honest truth is, esophageal manometry is currently underutilized because it is notoriously demanding technically. Right now, it requires manual recalibration, super careful positioning, and it's highly sensitive to artifacts, like even the patient's own heartbeat bouncing against the esophagus can mess up the readings. For a closed-loop system to rely on this data, we need massive technological upgrades. We are talking about smart catheters for automated calibration, integrating AI and machine learning to seamlessly filter out that cardiac noise, and most importantly, robust fail-safes. If the sensor loses signal even for a moment, the ventilator must instantly default back to a safe, conventional manual mode. And look, obviously, we are dealing with human lives here, so we can't just flip a switch and let a computer take over. The source material outlines a rigorous validation roadmap. Phase 1 requires extensive bench testing on high-fidelity lung simulators, covering everything from normal lungs to severe ARDS. Phase 2 is an advisory study right in the ICU, where the algorithm simply recommends settings to an expert clinician just to see if they agree. Finally, Phase 3 requires a full randomized controlled crossover trial to definitively prove that this automated system improves patient synchrony and saves lives better than human-directed ventilation. We've covered a ton of ground today, but it all comes back to this core takeaway. This theoretical framework represents a truly physiologically attractive step toward personalized, highly protective critical care. Esophageal pressure isn't just an extra data point. Its role in safety is paramount. It literally holds the key to the deepest levels of patient protection. So it leaves us with a pretty provocative question to think about. How long will it be until we look back at manually adjusting ventilators the exact same way we look back at driving cars without power steering? The autopilot era is coming. Keep learning and keep exploring.